really realize. Oh, by the way, Romendo can speak to this, but one really nice thing about being right next to the Math Science Center and having all the math classes in the same building is my office hours get utilized. Mm-hmm. They get utilized a lot. So I completely forgot to print out the practice test for you guys. I've just been swamped since I finished teaching my last class. So what I'm going to do, I'm going to email it out to you guys. If you want to come back with me to the office, I can print one out for you, or you can just wait. And then next time I'll have the answer key. We'll have a review. Are you guys all with me? Just make sure you guys understand. It was supposed to cover chapter 5, but we'll just do that after spring break, because you guys understand that take the test next Thursday, and then the next week after that is spring break.
That's what I do for a week.
Huh?
What do I do for a week?
Oh, I'm sure somebody's got a suggestion. I'm almost certain. There are some stuff you could do. I'm thinking about going to Idlewild. You guys know Idlewild?
Oh, I said Iowa.
No, I gotta take a little road trip to Iowa. If you've never been to Idlewild, it kicks so much ass. It's such a sleepy little town. Awesome freaking hikes. Jeez. Anyway.
For the 8-week courses, do you know if we still have class or do they skip that?
No. So the beautiful thing about what we've done now with spring break, it's been a while since I taught 8-week classes, but the suckiest thing about it was the first 8 week would end. I'd immediately start the next 8 week, and then there'd be spring break. It wouldn't be in the right. So now they always have spring break between the 2 8-week sessions. So if you're in an 8-week class, it is done next Friday. And then the next 8-week section starts the Monday after spring break. It is beautiful.
Yes. Spring break's
Yeah, so once we get to spring break, we are halfway through the semester. Yeah. Are you guys all with me? Yeah. It's a good little transition, huh? What have we done?
No, wait a minute.
Oh, I was going to say, what have we even done in this place? We are done. It's on this homework sheet.
May 25th.
Sure.
May 25th.
That's the last.
All the information in the homework sheet, one reason I do all that is because I can't keep it up here. It's no way to know. So, yeah. Okay. So let's finish up section 4.2. We got the tiniest little bit into section 4.2. Shut all this off. Okay. Let me set this dude up. Yeah, today I'm gonna do it up here. Why not? Yeah, I'm trying to transition my classes since everybody's surrounded by monitors. You guys, this is the one class that doesn't have a monitor there because we have cabinets. I'm trying to do on the overhead, even though I don't really like the overhead much. We'll see how it goes. Okay. So what we did last time, I did some base 10 pieces, and it kind of shows you. And it's sort of like what the little dude did with the blocks, but with the base 10 pieces, it's easier to see why I carry the 1. So here's something you guys could do with me. So if I wanted to add 27 and, what do you got, Jeff? 15, right? Base 10 pieces. I would have 2 what's here? 2 longs.
Logs.
And 7 little dudes. Okay. And then I'm going to add to it 15.
Oh,
5 little dudes, yeah. Okay. You can do it. There you go. Come on. Now we've done this a couple times. The very first time we did this, we did it with base 3 pieces. But what's the idea here when I add these together? Here's 5. How many of these, and again, this is all about making the base, correct? Here's 7. I should go this way. How many of these will it take to make this into a long? 3. Okay. So these together make another long. And I've already got 1, 2, 3 longs. You guys all with me? So I got 1, 2, 3 longs. I put these 3 with these 7, and I make another long. And of course, how many do I have left over? 2. So this creation of another long is exactly the carrying the 1. So if I do it, the algorithm that we all know, I do 2, there's the 2. I carry the 1, this is the 1 getting carried. That is the 1 getting carried, and it adds to the 3 that were already here. You guys see what I'm saying? You made this into a more physical idea. Collecting shapes, which is something that humans of young age love to do. Okay. You guys all semi with me. Okay, so this is a great first step to introduce why we carry the 1 in our shortcut algorithm, right? So this is the standard algorithm for adding numbers. So there's a few different ways to represent this. Let me see how it gets a little bit into it. So let me show you something. If I was going to do 116 plus 253, I'm not going to do that. There's something called a chip abacus. If I could just write, everybody's life would be so much easier. You guys ever heard of an abacus?
Yes.
Where you slide the
Abacus.
Yes.
Those things actually are useful.
Yes.
I've never seen one used.
If you really know how to use it, you can do a lot of shit really quickly. And of course, the next thing after abacus was the slide rule. Has anybody ever heard of slide rule? Thankfully, I'm not old enough to have used those directly, but I do have a circular one somewhere. But it's basically the slide, and you get answers to certain math problems just because of the numbers that line up when you do certain things. Of course, we wouldn't have a clue how to use them because nobody ever showed you, right? But it's before we had calculators, so it was the next best thing. So this guy, the way this looks, it's not really an abacus. I'm sorry, I'm not going to suddenly give you everybody an abacus, but
You should.
I should. I know. My budget has got so much room. Yeah. So if I do this, this is sort of like what little dude was doing in a way, but not really. So if I represent each of these with a chip, which is why it's called a chip abacus. So I got 100 in here and 200 in there. I got 110 here. I got 5 10s here. I've got 6 1s here, and I've got 3 1s here. Yes, and I'm not sure why I'm writing so tiny. Oh boy. Good. There we go. Maybe. Come back to me.
Would you have an abacus for next month?
I have a Himalayan bead calendar, which kind of looks like an abacus, but it's just for keeping track of the day, month, and year. But if you look at it, it looks like an abacus, but it's like
I
this.
see that too.
Yeah, it's neat. Do I have an abacus? No. Yes.
Is the abacus the one where like the kids go like this in their heads?
Well,
Oh,
here.
yeah, yeah. Because you normally it's this way, and you move things back and forth on little lines, and they each represent a different
Yeah,
thing.
like there's videos of like kids doing math in their head and they go like this.
Oh,
they're moving the
I'm not sure if
abacus.
that's necessarily related to the abacus.
It's just.
It is? Oh, okay. There you go. Then it must be. Yeah.
I think I have an abacus at home. Can I bring it in?
Oh yeah, sweet. Please. Kick ass. Okay. So then all this is counting again. 3, 6, crazy. 9, okay. This is a little less concrete. This is a little bit more abstract, but it's still counting, right? Yes.
Like instead of if you had like 254 and you had 10. How
Yeah. So now we're going to talk about how to, what do I do if I have to carry something, right? Good. That's our next thing we're going to do. So what if I had, yeah, you give me a problem. I'm ready.
257 plus 340.
Okay, cool. 11. 257, 349, 100, 10, 1, 200s and 300s, 5 10s and 4 10s. Jeff, they know what you're doing. I know. What was that, 9? If I can just read my own writing, it's pretty bad. Okay. Did I tell you guys the day I can't read my writing is the day I'm going to retire? So I might retire young. We'll see. Or, you know,
Tomorrow.
retire less old, I guess. Or tomorrow. Be quiet. Right now, I'm serious. Right now, I'm out here. So what can we show happens here? We can kind of do exactly what we did with the base 10 pieces. Still the same idea. It's still almost the same thing. It's just a little less concrete. So I've got 9 here. So of course, if I just suck in one of these, and apologies for sucking in, but this will make one more here. Is that cool? Those 10 are now 10. So this should show up in the column that has the number of 10s. This is still not carrying in an abstract way because they know this is where the hundreds go, this is where the 10s go, this is where the ones go. So if I put 10 of these together, that's another 10. So I put one more 10 here. Is everybody with me? Maybe? Okay. Now what happens here? Now. 5, that's a 10 again. 10 10s is 100, yes?
Yeah.
So I don't have these anymore, I don't have these anymore. So what do I end up with? 6? 0? 6. And is that the right answer? Thank you, God. So again, it isn't, I want you to realize carrying the 1 is unbelievably abstract. This isn't carrying the 1, but you can see how you can make connections and say, a shortcut way to do this is to just put a 1, meaning you just made another 10. Then carry a 1 again, you just made another 100. You guys follow? A student could definitely understand this, especially if somebody was able to draw better than me. But if I add these, so they got 6, and they took these and they put it in this column instead, and it was 1 more 10. So you say, okay, you have 1 more 10. And then those all made 1 more 10, and you're like, okay, so I got 1 more 100. 10 times 10. I like it. So a lot of parents don't understand how truly abstract that idea is, just putting a 1 up there. What the shit is it doing there? Why has it got to be there? What's it mean? I don't know. So you got to kind of lead a student in that direction. So then when they get there, they're like, okay, that's just what I did with the things. Okay, good. All right. Let me see. Nah, that one's not as good. Let's not do that one. So what about subtraction? Very quickly. So this, of course, is where we're going to have to introduce the idea of. So with addition is carrying the 1. With subtraction, I might have to borrow, right? So if I have like, let's do an example. Yeah, sure. 408 minus 153, and I want to do base 10 pieces. I'm zoomed in way too much. It'll come back. There you go. Okay. All right, that's base 10 pieces. So I'd have, no, Jeff, I got 408. So what do I need? 4 whats? 4 flats. No longs and 8 units. Okay. And from there, I want to take away 153, right? Okay. So let me write this a little better. I have 4 flats, no longs, and 8 units. They become little D's, but too bad. And I want to subtract 153. Now, what's the immediate problem? I could take 3 away from here, no problem, right? So I could take 3 away. That's so far so good.
And then you could just take a flat and make
Good, yeah.
5 long.
So I borrow a flat from this guy. And again, this is still very physical. It is not as physical as 400 blocks, but you do not want your kid on the floor 400 blocks taking on, But this is not the algorithm. It's still physical, but you can start to use the language that you're going to use later. You can say, okay, let's borrow one of these flats, and what can you do with it? Like you're going to say, you can break it up. You should just make a line. Jeff. What is that? 4, 5, 6, 7, 9, 10. Okay. So take that, break it up. So now can I take 50 away from 5 of those away? Yes. You can do it, Jeff. Choo choo. All right. And then I can take 1 of these away. So then I'm left with 200. 50, 5. How you guys doing? So the beautiful thing is, this is still physical. They are literally taking stuff away, right? You can have them pick this stuff up and take it away. The borrowing, you can say, yeah, let's borrow one of these guys, break them up. So then, because the problem is we don't have any longs to take away. I'm supposed to somehow take 5 longs away, and I don't have any. This guy's got 10 of them. Shit, let's break him up. Then I can take some longs away. All right, I like it. Okay. And of course, we all know the way to do this: 10, 3, and then you can make the connections. That 10 is literally these 10 here. Okay, I like it. Now, I could also do this with the abacus approach. So I did 408. Good Lord. It's a weird effect, a weird reaction to hail. Alright, I live another day. So if I use this, I can do 408. Oh, I'm dying. What we normally do is we quickly pass away. Hold on.
Don't do that.
Almost.
We still need to grade our papers,
I'm
but
almost
not yet.
I have to still.
You got a good,
You gotta give us grades.
You know what, before you die, can you at least
Wait,
set
wait.
all of our grades to A's?
Okay. I want to make a point.
What's your
There we
password?
I told you a story about anyway.
It's not this one. Is this one, or it's like F you everybody?
Yeah, okay, I told you that story. All right. So can you guys real quick just represent this in the 408 in here for me? Quickly before that, lose my voice again. Let's see. Oh, is it working? Oh. So this is a little bit different. We put the 153 underneath just to kind of remind us how many we got to take away. Again, if we start here, we can certainly take 3 away, but then we hit an immediate problem here again. So just, I don't know if you all understand, the differences in the approaches seem very slight, and that's on purpose. The base 10 pieces will be actual physical pieces. You can actually, this is kind of a step away from there, but it's still not completely abstract, because they still know this means 100, and then you can remind them, well, how many 10s are in 100? And they'll say, okay, 10. So then I can take one of these to give myself 10. And then it's pretty easy from there. And the whole idea is I can't take 5 away from nothing. Okay, you guys all with me? Nothing too amazing happening. So now I can take 1 away from these guys, so I'm left with 2. I can take 5 away from these guys, and I'm left with 5. And I already took the 3 away, and I was left with 5. So there's the 255 again. Okay. And it's these kind of problems that parents see on worksheets that students have to do for homework, and they say, why don't they just show you borrow? What the hell are they doing, these crazy ass teachers? So the great thing about teaching college is I don't have to deal with any freaking parents. But sometimes I do wish I could. In some situations, most of the time I only think that, but you're gonna have to deal with the parent not understanding the point of your work. And this is where you're like, oh good, become more involved with your student, fantastic. Get in touch with me. You guys are gonna want to be talking with the parents, which is gonna suck, because you're gonna have several sets of parents for so many students. Okay. Now, what about multiplication? If I want to do it with the chip abacus, and I want to do, let's say, 4 times 122. This is a little silly because it's really just the idea of repeated addition. So if you put 122 and you just do it 4 times. And then you just collect at the bottom, right? And of course this problem specifically does not involve any carrying, but it's pretty simple to see what would happen if I needed to carry. So what did I just do? I wrote 122 in the chip abacus 4 times. So then I just had to add the chips, right? Or did I do it 5? No, I did 4 times. 4, 88. Okay.
Very similar to like the array.
Beautiful. Yeah, it's funny you say that, because we're about to show, okay, I'm about to show something kind of nifty.
You got some dastardly bees.
Yes. Okay. So if I wanted to do one that involved, let's just do a smaller one that involves some carrying. This one gets interesting because I start off with the 10s and the 1s. Right, so if I can do 60, why'd you pick 9, Jeff? 69, and then I gotta do it 3 times. Okay, got a little bit lighter there at the bottom. I can still now, I've turned this multiplication problem, of course, into an addition problem, and it's still just counting the chips up. But when I start to add these up, I'm going to quickly see some issues, yes? So I'm going to get 9, 18, 27. So I can see that this would make another 10. We just put it here in the middle. And then another 9, you could do it, Jeff, plus 1 would make another 10. Yes? You guys kind of with me? And again, what is that related to? If I actually just did 69 times 3 like this, what would I put here? 7. And that's these 7 here. And of course I would carry
The 2.
2, because 3 times 9 is 27, and that's exactly physically those 2 that I just put over there. You guys see that? Now for us, we know this. I can compare backwards. For a student, they want to learn this, and then you can show them why this makes sense, this carrying thing. Okay. And you can do the same thing here, and you have to introduce a hundreds place now, because now if you collect 10 of these, you can make a little dot in the hundreds place. Are you guys all with me? A little bit, okay. I don't want to spend too much on the little tiny dots. So let me show you this. This is kind of nifty. If I wanted to multiply, let's see. Let's start off small. 13 times 11. Now, what I'm about to do is very similar to something we've done before. If I want to do 13 times 11, couldn't I make a box that's 13 this way and 11 this way? Right? Okay, so here's what I can do. How do I represent 13 in base 10 pieces? I would have
1 long.
1 long,
3 units.
3 units. How would it represent 11? Bless you.
One log, 1 unit.
1 long, 1 unit. Okay, and this gets nifty. So what I'm gonna draw here is something that's the same length as that one and the same width as that one. That of course is
100.
flat, which is 100, yeah. Here, same length as this one, same width as that one. Here, same length, same width. 1, 2, 3. Not sure if you guys are with me or not. So do you agree with me that these all have the same and the same? You guys with me?
Wow, that's weird.
Stay with me now. And then this times this, they're each gonna be. Alright, now can you collect for me what I just got? This is 100,
43.
43. 143. Is that what 13 times 11 is?
May you do it if you want.
Yeah, of course. Now, just to show you a computer-generated version of what I'm doing that you could actually tell what's going on. Maybe, let me see. You guys got that one a little bit? I really want you to understand the idea. I gotta draw a shape here that's the same length as this and the same width as that one. And we all know 10 times 10 is 100. This is just a beautiful geometric, visual approach to why that's true. So in the book, I don't know why they made this so tiny, but they did.
Is this gonna be on the test?
Huh?
Is this gonna be on the test?
Everything I talk about could be on the test.
But I said is. Not could it.
Very teacher answer, yes? Yes. There's 2 reasons I can't answer that question, because I want you to study everything and because I don't even know yet myself.
Oh, okay.
So the quick answer is everything I'm talking about can be on the test. So look here, this is 12. I'm sorry, what is the problem they're trying to 12 times 34. There we go. So I think they started this on the page before. Yes, 12 times 34. So 34 times 12. So they wrote 3 longs, 4 little dudes, 1 long, 2 little dudes, and then they kind of exactly like we just did. It's got to be the same length and the same width. Same length as this guy and the same width as this guy. And then it's just gathering all of the pieces together at the end. So you get 300, you get 80, you get 40, and you get 8. So 300, where do they actually do it? Wait, that's 60, I can't see. All right. So you do 300, stay with me now. 300 plus 40 plus 60 plus 8, and you get the answer. Okay. Now again, that's longer than just 34 times 12, the way that we know we can do it. But they're not born knowing how to do that. Oh, sure. Just to show you one that's kind of well drawn. Unfairly, because they use the computer. So, and then you got my thing here. Now, I will tell you this. I'm not overly concerned with doing this kind of problem, because can you tell this gets really out of hand quickly? Can you imagine what it would be like trying to do 1,497, for example, times something? That would be insane. Because then you'd have to go to, let me see how I can explain this. You'd have to go to a dimension we can't represent. So this idea quickly loses merit, but at that point, you're not going to go to that number. It wouldn't make sense to go to this number because you're just getting the idea. So of course you're going to start with smaller numbers. Build an idea and then build up. Okay. Now, how about division? Let me ask you guys here. Can you represent this in base 10 pieces? Okay. And then I'm going to divide by 3. So represent 48 in base 10 pieces.
Only.
So flats, longs, units, yeah.
Like, in a specific
No, just representatives, yeah. Yeah, division cannot work in a rectangular array, sure, Jeff. Array too easily. Now, what's really interesting is, you guys help me out. If I had to do this long division, where would you start? The 4s. Okay, so when we do this physical, we start with these guys. So if I group, now here's the idea.
I mean, they probably learned how to pick up the desk.
That's an option, but the when I'm dividing, so why is 6 divided by 3 2? Not just because 2 times 3 is 6, because 6 has 2 groups of 3 in it. Yes, that's another way to look at it. So I'm grouping all of my symbols in 3s, and then I'm counting how many groups of 3. So if I look at my hundreds. If I look at my 10s, I can group these guys. So I have one group of 3 there. This is my 10s place. Is everybody with me? Okay. What do we do with this guy left over here? This poor little dude. Chop him up. Oh man. Okay. Too bad for you. Chop him up. Okay. And then we just. What do we do?
Divide them into 3s.
Yeah. So there's 1, 2, 3, 4, 5, 6. Are you guys with me on that? Is that? So really, this is a version of division that's like you have 48 things, and you want to divide them so that you have 3 on each team. How many teams will you have at the end? That's really kind of physically what we're doing. Does that make sense?
The answer is 8.
Huh?
Is the answer 8?
No. The answer is 16.
1, 2.
So real quick, no. So I have one group of 10s,
Yes. Got it.
and then I have, when I broke this guy up, I ended up with 6
6
groups of
ones.
ones, of like 3 ones, yeah. Are you guys with me on this? Alright. Now obviously, this also breaks down. You don't want to do very large numbers. There wouldn't be any point to it, because you're just trying to introduce an idea, and then with the big ass numbers, you can use the full division algorithm, right? Do you guys realize, every now and again I'll have somebody, so when I teach pre-calculus, very quickly, I don't know if any of you guys ever did this. I think I brought this up once before. I teach them how to divide polynomials. Like long division of x cubed plus 4x squared plus 7x plus 1 divided by x squared minus 1. Long division. You guys kind of. We're not going to do that here, okay? My only point is, when I set it up, I use the normal algorithm for division. You put a number, then you put the bar, and then you put the number inside, right? I still remember it was about, I think it was 2007 or something. I had a student from Russia. She was born in Russia. She was brought up in Russia. She came over to the States like 5 years before that, whatever. She had never seen that shit before. They are taught how to long divide. They don't go this way, they go this way. And it's really nifty. And to be honest, I could even show you right now because I don't do it that way. So every time I got a student that didn't do it, I'd always ask, does everybody do division this way? If you don't, it's fine. Just let me know. And then I'd ask them, can you show me again how you do it? Because I always forget. I guess am I with me? Okay. So no matter what way you divide, the idea is the same. Can somebody remind me what's the basic idea of division? Multiplication is repeated addition, so division is repeated subtraction. I love it. So we're trying to do something like, it doesn't matter, Jeff. 6,100, no, let's make it gross. 6132 divided by 7. Like, divided by 7, yep.
6
So if I set this
It's
up,
not too gross.
instead of doing the full algorithm, they don't know that yet. You could just ask them, okay, how many 7s are in, give me an idea of how many 7s are in 60, so they could guess.
8.
Yeah, 8. That's how many are in 6100. So then you do 5600 minus that. So let me give you a better example, because this is almost the exact same as what we do. So let me give a larger divisor. 6132 divided by 200. Okay.
Probably go into 613 first.
So I would guess that there's 200 into 6,000. How many 200s are there in 6,000, do you think? Yeah, let's go with 12. I love it. What's 12 times 200? 12 times 2 is 2400. Is that cool? So this way it almost doesn't matter. Let me show you. Subtract. Right? You're going to get 3732. Is that okay? How many 200s in 3732? Somebody give me a guess. Any guess. It almost doesn't matter.
17.
Say again?
17.
17, okay. 17 times 2 is 17 times 2 is 34 with zeros at the end. Is that all right? 17 times 2 is 34. You put a couple zeros at the end. What do you get when you subtract those? 332. So how many 200s are in 332? 1. And that would be the remaining. So what is the actual quotient? Yeah, 30. Remainder 132. Well, let's check that. What's 30 times 200? 6,000. And of course, if I added 132 to it, it would become this. So the remainder is what is missing if you just multiply this number by that number. The remainder is the excess. This is not our division algorithm, correct? Do you see how it doesn't need you to be as precise? So this is kind of nice for students who are first learning how numbers kind of work together. They can give a guess. Even if the guess is wrong, it doesn't matter because eventually I'm going to get there. How do I know when I'm done? When the number is smaller than that guy, because then it can't take any 200s. You guys semi with me? Okay? And again, so what we're doing is we're stepping blocks, and then we're stepping one step above that, and then we're stepping one step above that. This is very abstract, but it is not our algorithm yet. And it is something that you can work with, because you could give a guess. Students can give a guess, and the beautiful thing about it is your guess isn't wrong unless that comes out to be more than this, in which case, guess a little smaller. Yep.
Could we keep doing the 6132 divided by 7?
Say what? Sorry?
Could we?
Yeah, this one was a little harder to show. This one almost, you just fall into the standard algorithm, right? I wanted a bigger divisor so I can kind of show the idea. Okay. I like it. So, of course, our actual algorithm, another way to do this, by the way, if I want to do 6132 divided by 200, but yeah. 6132 divided by 200. I could actually do exactly what we just said, which is repeated subtraction. Now this would drive us a little insane, because I do 6132 minus 200, and I would just keep going until I can't take 200 away anymore. That would be a little crazy. Do you guys agree? But you could be a little smarter. You could say, what if I subtract 5 at a time? So let me show you. So if I do 6132 and I subtract 5 200s at a time, yes? So I have to do it once, twice. You guys see what I'm doing? 3 times. 4 times would be a 2, 5 times would be a 1, 6 times would be, you guys kind of with me? So repeated subtraction, but in a kind of smart way, in a collected way. So don't subtract 200, you can subtract groups of 200. Let me stop for a minute. So again, could a student who has never seen the division algorithm before, could they manage this?
Yeah.
Yeah, totally. So we're trying to get them step by step to get to the point where they can handle a division algorithm. Okay. And then the kind of like the next thing you could do, let's see, do I want to do that part? Maybe. Yeah, maybe. Let me ask you this. If I wanted to divide 56 into, let's say, that's a little bit evil of a problem. 5198. What number do you guys, how do you figure out what to put here? So let me give you a hint. Something you guys do and you don't even know it is you look at the 5 and the 51 and you think, okay, maybe 10, but you know it's not 10. Why can't it be 10?
So that's 50.
Because that would make 560, yeah? Too much, so then you go, okay, it's gotta be 9. So very infrequently would we ever look at this entire thing. We actually just look at the first parts of the problem. You guys kinda with me on that? Okay, well, good. So that's a good thing to realize and to point out to your students. This is actually how you can look at this to get an idea for a guess for the first number. So if I do this, so let me do this. This is a little bit weird. 90. So if I do 90 times 56, it's a little bit gross. All right, but that'll be 0. All right, let me write this for you guys. 90 times 56, right? So it'll be 0, and then it'll be 4, and then it'll be 49. If I did that right. Did I do that right? Probably not. 50. There it was. And then, of course, when you subtract those, you get 148. 158, Jeff. I think it's been a long day. Now, this is a little bit weird too, right? You guys with me? But again, one little thing that's kind of weird for students is, when I put a 9 here and we put 504, I'm not even sure if you guys think about this, but you really are doing 90 times 56 fully. We just understand that there's no reason to include this place. But for a student just learning this stuff, okay, 90, okay, that's 50, 40, that's fantastic. I see 158. There's no like bringing down the 8. It's just directly subtracting 2 numbers. Now, what about 56 into 158? Yeah, you could try 3, right? If you do that, it's 168. If I did that in my head correctly. So then you'd say 2. So 2 times 56 is 112. So then you get 46. Now this is very strange up here, correct? But then I would just add, and I get 92, remainder 46. And of course we got our big ass R, right? From way back in the day. I know you all should know how to write that as fractions, but officially for us fractions don't exist yet. And what's really cool, just to kind of give you a preview, fractions have their own set of manipulatives, which are really kind of cool to get the idea of what a fraction represents and to kind of play with fractions more physically. Okay. Oh, cool. They talk about that part right there. Good, perfect. Okay, so just to kind of show you where we ended up. So we finished section 4.2. At the end, they finally get to the standard algorithm for division. Just to kind of show you, they talk about intermediate algorithms. Here's the one kind of like even more stacked up, like the problem I just did. Just to kind of give you an example. So 7 into 3159, they stack it up and then they add it up at the top. You guys see that? I like it. Let's see, blah, 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 blah. And here, this is a beautiful little example. This was the multiplication part, but we have the first step algorithm, second step algorithm, and then the standard algorithm. So in the first step algorithm, what's going on here? Yeah, 4 times 2 is 8. Where did they get the 60 from? 2 times 30, I love it. And again, so this is going to be a little weird to try to get you to understand, but when I see that 3, when we do 2 times 3, we just think 3 and we put it in the correct place. But a student needs to know that 3 is 30. So it's double 30 is 60. Where'd 40 come from? 10 times 4. And then, of course, 300.
But 30.
10 times 30. Yeah, right? Okay, I like it. And this is really not far away from this. Correct? This is very close to this, to the standard algorithm. And then this, of course, is just kind of doing two things. And this is 34 times 2, and this would be 34 times 10. Okay, which is basically just about the standard algorithm right there anyway. Are you guys all with me? A little bit? Okay. Okay, so again, the test will be I'll have one problem from section 1-2. 1-2 is everybody's favorite.
The word problem.
Yeah. I'll have one problem from section 1-2, and I'll even tell you, let me see. I won't tell you what it is, but I will tell you it would be most likely related to looking for a pattern. Really? Not like the, not like this problem here. Yes?
Okay.
Okay. That gets freaky down here, I understand. And then of course there's chapter 3, and that's the one I gave you some of the notes for. And chapter 4 we just finished. That's the one that's got compensation and all that kind of business. So again, just remind you guys, I'm gonna put the practice test up on Canvas. I'll email you about it at least, if not email it to you directly. And if you want a hard copy, you can come into the office right now, but. A what now? Yeah, of course. Yeah. No, I'll have it with me next Tuesday.
Can I get my quiz?
Oh yeah.